Hello everyone, my name is George Kalamatinos and I'm a PhD student at Uppsala University. In this video, I will talk to you about our work entitled Proportionality Spatial Keyword Search. Co-authors of this work are George Fakas and Nikos Mamoulis. Currently, there are many online datasets available that contain spatial objects, that is, entities that are associated with a location. Some examples are DBpedia and Yago, spatial Hadoop datasets, and datasets from social networks like Google and Flickr. These spatial objects are also associated with some context, for example, descriptive tags or linked entities. An example, the object P1 is a museum in Stockholm with a location and seen on this map. It can be associated with a few keywords or be semantically connected to other objects. A spatial retrieval framework needs to take advantage of both the location and the context of these entities to produce useful results. Let's consider an example of a user query to such a dataset. The user could submit a query containing a location Q and the keyword museum. As we can see on the map, there are 4 candidate places which contain the keyword museum in the area close to the query location. A relevance-based framework would return places P1, 2, and 3, which are the closest to the query and are also relevant. This is not always the most desired result, as the suggestions can be concentrated in the same region and contain mostly historical museums. We can consider an improvement on this query result by applying a diversified framework. This could return the places P1, 3, and 4, which are all located in different areas and are all museums of different types. This result is more varied both spatially and contextually. However, the user does not get any information about how representative these places are of the area around the query. In this work, we argue that there is still useful information in the fact that an area might have a higher density of candidate places or higher density of places of a specific type. Thus, we propose a proportional retrieval framework. This could return places P1, 2, and 4, reflecting the higher density of spatial objects in the northeastern region, but at the same time including a result from an opposite direction. It also includes 2 historical museums, which is representative of their frequency, but also includes a museum of a different type. Let's now formally define the k-proportional semantic places problem. Assuming, assuming a query location, Q, an input set of a number of places, with their location and contextual set and a relevance score, we want to retrieve a result set R of lowercase k number of places, which are both relevant and representative of the input set. To measure this property, we define the holistic proportionality score, which is dependent on the location and context of places both in the input set and in the result set, and is a weighted average of the relevance score of a place and its proportionality score. We have proved that the problem of finding the subset R of places with the highest HPF score is NP-hard. For this purpose, we have adapted already existing grid diversification algorithms to create a proportionality framework and solve KPSP. The proportionality score has a spatial and contextual component. For each component, the rationale is to favor places that are similar to the input set, but diverse to the result set. For example, a place which is close to an area where the majority of places in the input set are located, but at the same time is further from the rest of the places in the result set, would have a high score in the spatial proportionality component. The contextual proportionality score with respect to the input set, PCS, is the sum of a place's contextual similarity scores with the rest of the elements of the input set S. Similarly, the contextual proportionality score with respect to the result set R, that's the score PCR, is the sum of a place's contextual similarity scores with the rest of the elements of the result set R. The set-wise spatial proportionality scores are defined analogously. The contextual component uses the Jaccard coefficient as a contextual similarity measure between the contextual sets of two places. The spatial component uses the complement of Ptolemy's distance as a spatial similarity measure, which we have previously proposed in our work in VLTBJ. In that way, places in the same direction to the query and close to each other, like P2 and P3 in this figure, are considered more similar than places in different directions, like P1 and P3. As it might have become apparent, in contrast to diversity, proportionality as a concept depends on the similarities between all candidate places within an input set to determine if a certain place is a representative of the whole set. The number of candidate places in an area of interest can be large, thus creating a high computational load. For this purpose, we introduce novel algorithms to efficiently calculate the aggregate proportionality scores for larger set sizes. We use these algorithms as part of a proportionality framework which adapts existing greedy algorithms to return the subset of suggestions. Our problem definition necessitates the pairwise comparison between all places in S to compute all the pairwise HPF scores and determine the subset R. Our framework consists of two steps. First, we compute the pairwise HPF scores for all places in S. This involves a quadratic number of comparisons. We employ our tailored algorithms to reduce the computational load in practice. The computation of the optimal set R is NP-hard. For this reason, we adopt two existing greedy algorithms that can approximate the optimal result set. YADU iteratively constructs the result set R by selecting each time the place from S that maximizes the contribution it can make towards the setwise HPF score. On the other hand, ABP greedily constructs the result set R by iteratively selecting the pair of places PI-PJ with the largest pairwise HPF score. Both algorithms use thresholds for faster termination. Now let's focus on our proposed algorithms that facilitate the computation of the proportionality components. To compute the contextual proportionality score of a place P with respect to the input set, we need to compute all the pairwise Jaccard similarities between the places in S. To compute these scores efficiently, we propose the microset Jaccard hashing algorithm. MSJH facilitates the comparison of sets which have common elements and prune others. We can see how MSJH works in the following example. We consider a set S of places P1 through 5 with their respective contextual sets of elements A through I. We first construct the hash table MSHC by creating an inverted list for each element with the sets wherein the element appears. We do so in reverse order to more clearly illustrate the stopping conditions. Then we iteratively compute the intersection of all sets by incrementing the relevant array element. We terminate each iteration when an element appears in a set that has already been considered. In that way, the contextual set of P3, for example, does not add any operations to the computation as it has no common elements with other sets. We do a final pass on the array to calculate the Jaccard similarities. Since we have already computed the intersection of the sets, we need to divide by the union size of each pair of places. We can infer the union by the set sizes and the already calculated intersection size. This algorithm has a worst case cost of k squared times the contextual set size, but as we show experimentally, practical cases do not have highly overlapping contextual sets. To compute the spatial proportionality score of a place with respect to the input set S, we need to compute all the pairwise Ptolemy's distances between each place and all the rest of the places in the input set. To efficiently compute this scores, we propose grid-based algorithms. These algorithms approximate the spatial similarity of a place with the input set S. The main concept is to approximate the Ptolemy's distances by using pre-computed uh, distances between cells of a grid instead of the actual coordinates. We can see how the grid algorithm works in the following example. First, we define a grid area centered on the query location. The side of the grid corresponds to double the distance from the first point from the query location. We can define the density of the grid by selecting the grid size, that's the number of cells that comprise it, and each cell's location is identified as its center. Next, we assign each place of the input set to a cell and increment the cardinality of this cell according to how many places exist within it. As you can see, for example, we have assigned 7 to this cell that contains 7 places and 1 to the neighboring cell that only contains 1 place. All the pairwise Ptolemy's distances between cell centers can be pre-computed and also be readily available at runtime. That is because distance is not affected by changes in scale. Now we are able to calculate the spatial proportionality with respect to places in the input set of any place using the cardinality of the cell and the precomputed array of Ptolemy's distances. In that way, we perform all the pairwise comparisons for the cells of the grid that contain places instead of comparing between all the places of the input set. The time complexity for the whole process in the worst case is k squared. That is for the edge case where all places are allocated to unique cells. In practical cases where the size of the grid is smaller than the number of candidate places, the places are grouped in cells in more than one at a time. The space required is O of k at runtime together with O of size G max, which would be a larger pre-computed grid to accommodate different sizes of G for different queries. We also investigate the variation using a radial grid. However, this suffered from a worse approximation error due to the larger radial cell sizes in areas further from the query. To demonstrate the efficiency and approximation quality of our proposed proportionality framework, we have run a number of experiments on prominent real-world datasets, namely DBpedia and Yago. For each dataset, we have generated 100 queries by retrieving sets of candidate places from different metropolitan cities around the world. For all experiments, we have varied the size of the input set, the result set, and that of the contextual set sizes for each place. First, we tested the efficiency of MSJH in calculating the proportionality scores for varying input set and contextual set sizes. We did that against a baseline of directly computing all pairs of contextual similarities. In figure A, we can see that in DBpedia, MSJH scales significantly better than the baseline, with improvements of up to one order of magnitude for k for the input set size equal to 1000. At the same time, it is not significantly affected by the size of the contextual sets, as shown in figure B. For the calculation of spatial proportionality, we consider the efficiency of the grid algorithm against a baseline of directly computing all the proportionality scores for each place in the input set. Both grid algorithms are significantly more efficient than the baseline, achieving a consistently better performance of 1 up to 3 orders of magnitude for larger values of the input set size. We also observe in figure B that the size of the grid only marginally affects the efficiency of the algorithms. The grid algorithm is approximating the true value of the Ptolemy's distances, so we now look at the quality of this approximation against a baseline against exact values. For the default grid size of 100, the approximation of the grid algorithm is steadily in the 5% range. The approximation quality improves for larger grid sizes, but only marginally. The alternative radial grid suffers from a high approximation error due to the less densely grouped places further from the query. We also tested the efficiency of our algorithms as part of a complete retrieval framework based on existing grid algorithms EADU and ABP. We can observe that for all settings, the cost of our optimized version is about one order of magnitude lower than the baseline version, and the difference tends to increase for larger sizes of the input set. This is mainly due to the improvements in the spatial proportionality calculations. At the same time, it's unaffected by the result size. Given that our optimized framework involves an approximation of the spatial proportionality score, we also test the effect of this approximation in the retrieval framework as a whole. Thus, we compare the holistic proportionality scores achieved by the optimized framework compared to the baseline one. The approximation compromise uh, due to the grid algorithm is minor, with values of 0.8% for EADU and 6.6% for ABP for the default settings. Finally, we conducted a user evaluation to attest for the preference of users for proportional results. We presented um, we presented them with 10 random queries from both datasets and the results according to the three alternative frameworks. That is, results based on relevance, diversity, and proportionality. We asked them to submit a score for their overall preference, ranking, and the usability of the results according to three tasks. The results show a clear preference to the proportional results, both in general terms and in terms of ranking. We can also see a preference of users for the proportional results for 2 out of 3 tasks. Reaching the end, I will summarize the central points of our work. We have introduced the NP-hard problem of proportionality in location-based retrieval for places with context. We have proposed a generic algorithmic framework that adapts existing greedy diversification algorithms. We have proposed a novel efficient algorithm for the calculation of all Jacquard similarities between all objects of a collection. We have proposed novel efficient algorithms for the calculation of Ptolemy's distances between all objects of a collection. Finally, we presented a thorough evaluation of the effectiveness and efficiency of the proposed algorithms and framework on real-world datasets. Thank you for your attention. We would be happy to address any of your questions during the author session. You can also reach us via email.